Okay, we're back here at the top of the hour. I think that to stay on schedule, we'll get going. I'm very happy to introduce to you Professor Michael Jordan, who's giving the summit keynote address today. So if I don't think Dr. Jordan needs any introduction, but I will anyway. He's the Pihong Chen Distinguished Professor in the Department of Electrical Engineering and Computer Science and the Department of Statistics at UC Berkeley. He received his master's in mathematics from Arizona State University and his PhD in cognitive science from UC San Diego. Prior to his appointment at Berkeley, he was also a professor at MIT. His research interests bridge the computational, statistical, cognitive, biological, and social sciences. He's a prolific author in these areas. If you look at his Google Scholar, his publications have received nearly 250,000 citations. These works have received many awards and recognitions. I don't have time to list all of them. We want to hear what he has to say, but I will list a few of them. Professor Jordan is a member of the National Academy of Sciences, a member of the National Academy of Engineering, and a member of the American Academy of Arts and Sciences, and a foreign member of the Royal Society. He is a fellow of the American Association for Advancement of Science. He was a plenary lecturer at the International Congress of Mathematics in 2018. He received the Ulf Grenander Prize for the American Mathematical Society in 2021, the IEEE John Van Neumann Medal in 2020, the IJCAI Research Excellence Award in 2016, and also in 2016, he was named the most influential computer scientist in the world in an article in Science. So it is our great pleasure to have Dr. Jordan with us today. As you can see on the screen, he's going to talk to us about machine learning as statistical learning, computational, inferential, and economic perspectives. So thank you on behalf of the organizing committee, Dr. Jordan, for taking the time to be with us today, not just for this keynote, but also for the panel discussion that's coming up in an hour or so. So thank you.
Thank you very much. Thanks for the introduction, and really my pleasure to join you. If there are any logistical glitches with slides or audio, please let me know. Okay. Yes, anyway, glad to be here. Glad to have a discussion with you this morning. I do think you are onto something as a community with this notion of statistical engineering. And really, I guess one of the things I want to do is talk about the scope of what that might be. And I'm going to be really taking a perspective of someone who works a lot in industry. I do think that our field, whatever you want to call it, is an outward looking field. And really the question is, what's on the other side of that outward look? Who do we engage with and for what purpose? So what are the phenomena of the era? And so on. And so I have the phrase machine learning here, just because in the outside world, if you go to companies, they often use the phrase machine learning to describe what we might call statistical engineering. They also nowadays even more just use the phrase AI, sort of badly. So the question is not going to be to define those terms or delimit them per se or relate them. They really, I think, reflect the same underlying phenomenon. And I want to talk more about the phenomenon and then what might be the scope of this emerging phenomenon and how do we respond to it and what do we want to tackle as the full scope of it. So this is a slide I've been using for a few years now. In fact, before I was aware of some of the work that you folks have done. But I was trying to understand what this thing called machine learning was. Again, it's being used a lot in industry, and it kind of reflected at some point the need to have people who had both statistical education and computer science education. Then the word data science became used for a very similar set of issues. Academics then have scrambled around to kind of define each of these things and have curricula and so on. But I think that's somewhat missing the point. I think it really is driven by the outside world. And I think that the best metaphor eventually came to mind was that it wasn't an academic creation at all. It wasn't a new field of inference. It really was statistics kind of conceptually, but it had a different flavor. And I think it was akin to the difference between chemical engineering and chemistry. So, historically, pseudo-historically at least, in the 40s or 50s, chemical engineering emerged. It didn't exist before that as a discipline, but you already had explanatory principles. You had chemistry and fluid mechanics and quantum mechanics and so on. So you understood what happens when you put chemicals together. But what you didn't have is the notion of scale. I mean, you didn't have the notion of the ability to design and build a factory that would make products at scale for large numbers of people that would be economically viable and so on. So a field emerged as people were building factories. They also had a field emerged called chemical engineering. And it had its own mathematics to it. There, new thermodynamic principles at scale, new fluid flow principles, and so on, needed to be developed. And if you are a chemical engineering student, you'll study that mathematics. So it's not just engineering; it has its own mathematical ideas in it. Electrical engineering, I know a little less about the history, but clearly there was electromagnetism before that. There was Maxwell's equations and some understanding of electrical flows. But the idea of putting circuits together and having power brought to homes and so on required, again, brand new ideas. And if you study electrical engineering, you engage in that kind of mathematics of electrical engineering. So I think that we are seeing an emergence of something new that has an engineering flavor. It's based on flows, it's based on networks. Computer networks underlie all of it, but it's not about the computer networks per se. It's about the value and the data that flow over those networks and how they link people. So this, I think, is the first engineering field that really where people and people's decisions and transactions and behavior is integrally part of the engineering discipline. It's not an afterthought or a secondary aspect of it. So, many companies have been, of course, building systems that do this. Companies that do e-commerce, companies that do finance, transportation, you name it, are building large, in fact, even planetary scale systems that are fundamentally based on inference and prediction and decision making under uncertainty and so on. So those artifacts, whatever you want to call them, they certainly have a statistical and an engineering flavor. You notice the word science doesn't appear here at all. And I think a slide we may talk about later that I also used is that I questioned why science becomes the priority for statistics, that scientific discovery is certainly the history of statistics. It's, we think of ourselves as embedding ourselves with teams to make scientific discoveries. But engineering is as important to the human species as science is. They obviously go together, but building artifacts in the real world that never existed before, I think civil engineering also, has changed our life more than just about anything you could imagine. So contributing to a new engineering discipline, its birth and its shaping seems really, really important to me, in addition to any role we play as helping scientists make discoveries. Okay, so today's talk, I want to emphasize the three foundational disciplines. It's often been emphasized that there's statistics and computer science kind of being brought together, but I'm going to emphasize in this talk economics. And this partly came again from being in industry and watching problem solving around the table, where a system was being designed, inferences were made, data was being collected, and then it was being deployed in the real world, and suddenly interactions and strategic agents came into the focus and into play. Game theoretic concepts came out, and it was clear to me that that was just the tip of an iceberg, that there was a whole economic model needed to be understood and developed in concert with statistics and computer science. And if you think about the connections between these fields, of course, they already exist at some level, but they're really dyadic. So statistics merging, blending with economics, that's econometrics. But econometrics has had a limited goal. It's mostly about measuring economic phenomena. It's time series analysis, a bit of causal inference. It's less about designing economical systems. It's less about what's called mechanism design in economics, and it's also less about large-scale distributed computing and networks and so on. So it doesn't have much of the computer science algorithmic flavor that we might expect from a broader discipline. Similarly, statistics coming together with computer science, that's really machine learning. And I'm going to use the phrase machine learning broadly here. It's not just a class of techniques for making predictions. Someone who calls themselves a machine learning researcher generally will also talk about decision making around uncertainty and talk about building large-scale platforms and so on and so forth. Right, but what they kind of are missing, I think, is the economics perspective. They don't have the perspective of strategic agents who are possessing data, acting on data, having self-interested, having vested interest in the outcome of a data analysis. And I'd argue, in fact, statistics doesn't have very much of that perspective either. Now, economics with computer science, that has a name as well. That's called algorithmic game theory. And there are textbooks on this. That field exists. It's maybe less known to some of you, but it exists, and it has real contributions. A core part of that are things like algorithms for matching markets. So kind of the microeconomics meets computer science. Again, it's a dyadic connection. What it's missing is statistics. It tends to assume that things are known a priori and just worry about the algorithms and the stability properties. It's missing statistics. All right, so I hope the message was kind of going to be clear that emerging problems in real life blend all three of these perspectives. You have self-interested agents, you have strategic data gathering, you have to put that in an algorithm and computer platform, and you have to use statistical inferential perspectives to inform all of these things. So whatever you want to call all of this mix, there are real world problems that very much have this flavor. And so I want to emphasize in this talk kind of the economic side of it, because I think it's probably less emphasized, and at least to me, it's very much in scope. Okay, so let's use this phrase machine learning for a while. Again, I'm not trying to define it as a subset of anything or related to anything. If you want to place statistical engineering instead of machine learning here, that's perfectly fine. Let's just recognize that it has had a big impact on our world, and it's not easy just to define that impact. But pattern recognition is another terminology that's used to describe much of what the impact has revolved around. Platforms like TensorFlow and PyTorch have been essential. So the computer science contribution is in part to build large-scale platforms that run on commodity hardware and don't run just on one laptop, but run just as easily on 10,000 laptops and can be used for very, very large-scale data analysis. And so sometimes you don't hear people in industry even knowing that this is statistical prediction or inference. They just think of it as AI or machine learning because of the platform that calls it that, and they simply use it in that way. So they may be doing a linear regression or a logistic regression, thinking of that as AI and pattern recognition. So that's certainly one side of machine learning, and it's one side of statistics. But more broadly speaking, statistics and machine learning have a decision-making side. In statistics, we often start with decision theory, but then we move on quickly to inference and regression and so on. And I want to restore decision-making to its rightful place here. And also the machine learning people tend to not think about it less as well. They have a separate branch of ideas that don't make that much contact with pattern recognition. So we'll talk a little bit about individual high-stakes decisions and then get all the way to market mechanisms where lots of decisions are interacting and start to talk about what are the intellectual issues at play there. Okay, so just a slide to remind you of kind of what we might view as pattern recognition. This is a thing that's had a huge impact, at least in the real world. It's had an impact. It's certainly in our media. It's talked about a lot, and there are use cases in industry that are impressive. Whether it's going to have a huge impact on productivity going forward is not entirely clear, but probably. So deep learning has become the dominant paradigm here. It really is a form of regression. It requires input-output or covariate response pairs. It's fitting a surface to high-dimensional data, and it uses a gradient descent method to adjust the parameters of this. So it's very statistical in flavor, but you tend to be focused more on the output, the prediction, and less on the inferential properties of it. But that's just that's some people's focus. It's become so widely deployed that just really there's a subgroup focused on any aspect of it, including error bars and inferential things and model selection and you name it. So many real world examples: credit risk assignment, computer vision, robotics. All these problems in the real world are these architectures are being used. Okay, so I'll not say anything more about that. Let's just be aware that's kind of the context. All right, now let's turn to decisions. So you might think that a decision is kind of a thresholding of a pattern recognition device, and I'm going to argue that's not really a useful perspective in consequential real life decisions. So to be very concrete, let's consider you go to your doctor's office in a few years, and the doctor has available to them a large deep learning system that's been trained on all the world's medical data. So the hospitals have all aggregated their data, and just everything that's relevant to medicine has been put in there, and it's been used to train this neural net that makes predictions based on someone's body state, a prediction of their health status, or what the probability they're going to have various diseases, and recommend treatment options. So suppose you arrive and they measure 100,000 things about your body, including maybe they sequence your entire genome, and they put that into that neural network. and let's suppose that one of the outputs of that neural network is a prediction about heart disease, and based on all the historical data, that goes beyond what any human has ever looked at, if a number is over 0.7, that suggests you're about ready to have a heart attack and you should have an operation ASAP. And suppose your number is 0.701. Now you're over the threshold. You should just think of that as a decision by the smartest system ever built and just kind of adopt it. The answer is probably no. You're going to, first of all, you're going to make some inquiries, like what is the error bar on that? How sure are you of that at 0.701? And I don't mean just a little Gaussian error bar or a permutation test error, or a sampling error. It really has to do with where the data came from, how old are the data? Are they recently collected, maybe 10 years old? That would increase my uncertainty. Was it collected on a machine like the one used for me? Was it collected on people like me? And so on and so forth. And all those things should contribute to your notion of uncertainty. And in the context of the doctor's office, sitting and having a dialogue with a doctor, you may never write down these uncertainties, but in your mind, they're arising. And a good engineering system should kind of have them there. So somehow, like a database system that has notions of provenance, of where data came from, and metadata, as you started to have a dialogue about your particular decision, the error bar should be adjusted accordingly. Moreover, you're going to ask questions of your doctor about alternatives, alternative explanations. You're going to remember things you hadn't remembered before. For example, I had asthma when I was a child, or my parents had a heart condition. I forgot all about that, and now I remember it. And you're going to realize that that pattern recognition device did not have all the world's medical data in it, in the sense of it's in the moment of a particular decision about your heart disease. There's all kinds of new things that become relevant that weren't relevant before. And so a good doctor will then take that in as data effectively and readjust and make new predictions, effectively doing counterfactual analysis in the moment. And you will be reasoning in the moment about this in a dialogue with your doctor. And so a good statistical system should support all of this. It should be doing all of this adjustment and rerunning data analysis in the light of new information that's being discussed as part of that dialogue. So that's what real decision making is like, and reducing this to decision theory and a threshold between two Gaussians and all really damages the serious dialogue nature of a real world decision that's consequential for anyone in their real life. And it doesn't have to be medical, it could be anything. So today I'm going through many decisions, and they're at different scales. Some of them are on the scale of minutes or hours. Some of them are decisions I'm doing in my life at this period of time. All right, so there's consequences, there's counterfactuals, there's provenance, and so on. And any system that purports to aid in decisions has got to participate in this. So it's, moreover, it's not just my own decisions, it's me linked with other people across networks. Even the health system, if a drug is tried on someone somewhere and it works, the system should pretty quickly make that data available to other doctors to be used for other patients. So we're linked in some ad hoc sense, and the pandemic has kind of revealed this. We're linked by the decisions made for other people on us. And this happens over time, it happens asynchronously. And in the medical system, it's very ad hoc, all of these linkages, but in something like transportation or finance or commerce, it's less ad hoc. There really are real existing networks that make these kind of connections. So I'm starting to move towards economics as I'm in this discussion. If you start to make decisions in the real world, there will be interactions among the decisions. There'll be scarcity and competition. And so a good decision is no longer definable even in isolation. It depends on what other people are doing and depends on trade-offs. So now we're really in the world of economics. So let's again be very concrete to get there. Let's talk about recommendation systems. So this is definitely an engineering artifact. A recommendation system is a commodity piece of software that you can download. It takes in data in the form of a big matrix. For example, customers and the items they purchased, or viewers and the films they viewed, and so on. And you can analyze this data with some kind of a matrix-oriented analysis tool and make predictions effectively and treat them as recommendations for people. And you've all used these, for example, recommending books on Amazon or movies on Netflix, but they're used now throughout e-commerce. In fact, it's kind of a multi-billion-dollar contribution to productivity. So these are prediction devices. Are they really also, can you think of them as decision making? They do make recommendations after all. And I would argue that they're very ineffectual if you think about them in the real world. So imagine that you've developed an analysis, a recommendation system, and it's a piece of software that people can use in various business models. And suppose that everyone in some city is using your app. And so your app might maybe make movie recommendations to people like Netflix does. If everyone in some geographical region is using your app, then you could easily recommend the same movie to 100,000 people. And that's not a problem because there's no scarcity in the world of bits. You simply copy the bits to everybody. If you recommend the same book to everyone, I'm sure this happens to Amazon on many days. You recommend the same book to 100,000 people. And many of them might want to buy that book, and there's something called print on demand that allows you just simply to print as many copies as you need. So there's no scarcity there either. But is there really scarcity anymore? And of course there is. And so just think about an app now that makes restaurant recommendations. Right now, there's not very good apps for this. If you are in Shanghai and you're out on the street and you don't speak Mandarin very well, and you bring up some browser and say restaurants in Shanghai, you're going to get a lot of junk, a lot of advertisements, or a lot of irrelevant material. So really what needs to be happening there is you need a recommendation system that is a little more of a in the moment, recognizes where you are, your taste, and so on. All right, but let's suppose that someone's designed that and people are starting to use that in some city. It again could recommend the same restaurant to maybe 10,000 people. And now you've created congestion. People will all go there and they'll be unhappy they can't be served. Same thing if you're recommending streets to drivers. What's the fastest route to the airport? Well, if you recommend that route to a few people, no problem. If everyone's using your app, you'll send too much traffic down that street and create congestion. Recommending stock purchase to people, you can destabilize the market this way and so on. So how do you fix this? And here I really think that Silicon Valley doesn't have good ideas about this. They think about this as a load balancing problem. The system made the best predictions it could, and now you have to balance that in some way, be fair. And even worse, Silicon Valley thinks that from your browsing history and doing statistical data analysis on your browsing history, they'll know enough about you that they can predict what you really would like, and they will send you to the restaurant you really prefer or down the street you prefer. And I hope that you agree this is really silly and it's moreover invasive. Really what we want to be involved in these kind of decisions is part of a market. And a market just means a connection between producers and consumers such that there are valuations that each person on one side values things on the other side, and the valuations may change and fluctuate in the moment depending on all kinds of other factors that we don't have access to that only the individual knows about. So I may have preferences for certain restaurants in the moment because I want to have a different experience, or I maybe think some friends might be there or whatever. You'll never know that about me. So really what I want in some sense is to be able to bid or be connected to the restaurants on the other side of the market. They'll look at me, I'll look at them. There will be essentially offers made, and I'll look at some particular restaurants on my cell phone in the app that have made an offer to me, and then I will accept one of those offers and they'll have made a transaction. So that's a matching market. Now it's at scale that we've never seen before in microeconomics. We're not used to millions or tens of millions of people connected to millions or hundreds of millions of entities, merchants or whatever. And similarly, drivers on one side, street segments on the other side. That's a matching market. And so if you value these things economically, you can start to actually see how that matching might be done. What's new here is that economists didn't typically talk about matching markets with data analysis. How much do I prefer a certain path to the airport? How much do I prefer certain restaurants? Well, I don't even know myself a priori. I have to have some experience in that. So I have to be a statistician analyzing my own data, starting to form my preferences in the context of what everyone else is doing, and perhaps sharing information. So whoever's building such a system, and they don't really exist that much, you can think of Uber as something like this. It matches drivers and riders, and it does use a modicum of data analysis, but just not very much, and it's not very effectual, at least certainly on one side of the market. But it has the flavor that I'm talking about. It's a data-oriented two-way market. So I think there'll be more and more of these things going forward. And my favorite example of this is music. So you'd think that we're in an era of, music, this is the world's best music market ever, because there's more music being made than ever before, and more people are listening to it than ever before. But there isn't a music market, really. There are a few famous musicians who are made super rich, and their music is promoted, but the long tail of most people is not in the market. And in fact, if you look at the data, 95% of the songs being listened to today in the US will be by artists you never heard of, and they're songs written in the last few months. So 95%. So everyone thinks that it's the famous musicians that we're all listening to, Beyonce or the Beatles or whatever, and that's just simply not true. And so a lot of the people making the music are, 16-year-olds who just do this as for fun on their laptop. They upload the songs. They're really good at it. People listen to the songs. They upload them to a site like SoundCloud, and then another site like Spotify will stream that to people. But now the market's gone. There's no connection between who wrote the song and made the song to who's listening to the song, and no transaction and no money. So there's no job available for the person who's actually providing economic value to all those people. Spotify makes a little bit of money because they created an artificial advertising market or a subscription market to make money for themselves, but they didn't create an actual market. So how do you create such a market? Should that be our job as statistical engineers? And I think, yes, it should be. This is a great example of something where a little bit of data analysis can go a long way. All right, and so in fact, it's not that hard to imagine doing this. So imagine that everyone who's a musician, meaning they uploaded some songs to some site like SoundCloud, is supplied with a dashboard at the end of the week. And the dashboard has a map on it of the United States. And every time one of your songs has been listened to, there's a dot on the map. So if you're reasonably popular, you'll see lots of dots. And it could be that you see that, my goodness, in Cleveland, Ohio, 10,000 people listened to my songs last week. For whatever reason, I'm popular there. Maybe someone liked my music and told their friends. And now there's economic value associated with that. If you contact the venue owners in Cleveland, will probably be aware of that. You're aware of it. You connect to the venue owners, and they say, "Well, come give a show here." And in fact, we even know who's listening to your music. Advertise to them that you're coming. You go there and give a show, and you make $20,000. And you do that 3 times during the year, and there's a salary for you. You're not becoming rich, but you have an actual salary. And the company that did this, it created a market, and they'd simply take a transaction fee. They don't have to do any advertising and so on. So you've created a market, and then markets become creative. So the musician can offer to go play at the wedding of someone who listened to their music, and for $10,000, and so on and so forth. So this exists actually already. The person there in the bottom right is named Steve Stout. He's an entrepreneur and kind of a brilliant person who conceived of a notion like this. United Masters is the company. You can go look at it on the web. It has 1 million musicians now that are active there. They didn't sign with record companies, but they signed with United Masters, and they retain their own songs, and their music is being listened to by for example, the NBA. If you go to the NBA website, you will hear music behind the clips, and that music is United Masters artists. So Steve here made the connection between the producer and the consumer. He helped make a market. So I was actually involved. Via a colleague, Steve and I connected up, and I helped talk about the design of a dashboard and the statistical engineering behind this company. So this is creating jobs for people. And you can imagine doing this not just in the US, but in Brazil, Africa, India, China. And you can imagine doing this for not just music, but for other kinds of entertainment or information flows. So I think this is actually a huge opportunity for anyone with a statistical engineering mindset. Again, the phrase AI is often being used for a lot of these kind of activities in industry. And there's a concern that AI is taking away jobs because it's kind of replicating what humans can do. This model is explicitly complementary. You're not doing what humans do, you're doing something complementary. You're connecting huge numbers of producers and consumers. That's something a computer can do, and you've added to human life. You, in fact, created more jobs. You didn't take away jobs. All right, so to do this as an engineering discipline, you have to take into account that you are creating markets here. and there's data and there's inferences and there's uncertainty about the market, and there may be robustness issues and so on. Are you creating a healthy market? Are you creating a damaging market? And so that's got to be part in scope for this emerging, let's call it discipline, if you will. All right, so some problems at the interface of statistical computing, whatever you want to call it, and econ. Multi-way markets in which individuals have to explore to learn their preferences. So exploration is a key part of decision side of learning. You don't know a priori what the right thing is. So in statistics, we don't talk a whole lot about it. We have bandit algorithms and there's A/B tests in industry. This is kind of where it comes out, but we don't have it in our curriculum very often to talk about the exploration side. We kind of wrap that into experimental design or something, but it's not really focused on, but it's critical in real life. Again, large-scale markets where you have to have some notion of a recommendation system, so information is shared among multiple people, because you can't have an experience of the entire market. You have to share information with like-minded people. Then all kinds of information sharing ideas, whether people are free riding or not, auctions where you learn preferences, and so on and so forth. In fact, privacy, fairness, and social good kind of issues are often talked about in the context of machine learning or statistical methods, but they have an economic side to them. You can't really talk about fairness until you talk about trade-offs and people's utilities and so on. All right, so the goal is to put all these things together in an academic discipline and make it relevant to industry. The last point is, just even apart from the statistical issues, that markets can be thought of as algorithms. They're making little local decisions and leading to a healthy functioning overall system, at least ideally. They're adaptive, they're robust, they can work at large scale and so on. So they're a powerful force that any engineering discipline should aspire to somehow making use of, corralling in some way, just like civil engineering may use of gravity. All right, and in fact, markets are not perfect. They have various failures. In the past, we've seen many market failures, and in the future, we'll have new kinds of markets based on statistics, and they will fail in new kinds of ways, and so we need to be thinking about that. All right, so the rest of my talk, I'm just going to give some vignettes of actual kind of research problems and proposed solutions to those problems to get a little bit of the flavor, again, of this bigger scope where you bring economics in contact with statistics, and then obviously algorithmic statistics. So the triad is present in all of these projects I'm going to be talking about. Okay, so let's go ahead and turn to that. So I may or may not get through all four of these. I really want to highlight a few points about each one of them. So I'm going to start with this problem of strategic classification. I have my students there, Tiana Zernich and Eric Mazumdar at Berkeley. All right, so classification is what you think it is. It's classifications is a terminology in statistics. Think of it as logistic regression with a binary response. But machine learning people use the phrase a lot too. You classify entities into one of two classes, good or bad, or true and false, and so on. So it's a high-dimensional, typically, problem where there's a large high-dimensional covariate and you're classifying entities into ones and zeros. All right, now we typically think of just gathering data, building a classifier, and then evaluating the classifier, and and so on and so forth. There's a pipeline of activity about how you structure the features, you use the covariates, how you measure the data, how you build it, how you validate it, and so on. And I'd argue that pipeline is missing a very, very key ingredient, which is that there's almost always feedback from the output to the input. Because the people who are involved in providing the data often are actually are self-interested, and they have a vested interest in the outcome. If they see an outcome they don't like, they're going to change their data to get an outcome they might prefer. That happens all the time, and if we don't recognize it, we're building bad systems. So consider health insurance applications. Health insurance companies want to assess your state of health to be able to decide how much to charge you. There's of course regulatory constraints and so on, but there is a data gathering aspect to this. And so they're going to try to gather data that's not easy for you to falsify. If it's really just filling out a form, you could lie. And since you probably know that you should say certain things if you have a desired outcome, then you'll say those things and you'll get a desired outcome. You'll pay less for your health insurance. Of course, health insurance companies are aware of this, so they are going to try to make it harder for you to lie. They'll collect data that's a little bit harder for you just to fudge. So an example of that might be the health insurance company will say, if you could opt in to give access to the acceleration of your cell phone. So if your cell phone is accelerating a lot during the day over time, that means you're moving a lot, you're not sedentary. And that can be used as a covariate, if you will, to predict health outcomes. Right, so this actually happened, it happens. It's a little bit hard for you to fake, but it's not that hard. So someone actually built a device you see on the right there. You stick your cell phone in it, and it moves the cell phone around in some random pattern all day long. And so the health insurance company thinks that you're exercising all day. It gives you a low score, a low price on your insurance. So you might think this is just silly, and more of this should be just ruled out as illegal or something. But you can't rule these things out. This is going to happen all the time in real life. It has to be part of the design of the system that's collecting this data and analyzing it. And this is called Goodhart's law in economics. It's well known. Here's an example of a poverty index score that was designed in 1994. On the upper left there, you see the score was well designed. You had a nice little Gaussian behavior there. But by 2003, it no longer looks Gaussian because people realized what was in the score, and they realized to make themselves appear more poor what to do, and people did that, and the whole distribution shifted over to the left in this very distinctly non-Gaussian way. So most people are now poor by this criterion, and of course, why do they want to be poor? Well, it's because they get more benefits in some sense. So this happens all the time. This is called Goodhart's law in economics, and I'd argue it's just extremely common. Here's another example of it. Uber drivers in Los Angeles. This was happened a few years ago. That Uber drivers colluded. They agreed that at Los Angeles airport at noon they would all turn off their cell phones. And as they turn off their cell phones, the pricing algorithm recognized there was not much supply, and it raised the price steadily over the next half hour. And 30 minutes later, everyone turned their cell phone back on, and they all got that high price and took the riders to the destination at the high price. And then this repeated from time to time. So, again, you could try to rule this out, make it illegal in some sense, or scold your drivers. But it's really just part of life. People are going to do this kind of thing all the time. All right, so good data science or statistical engineering should take this into account, and it's not just a data cleaning issue. It's not just bias. It's something deeper. All right, so it's really about feedback loops. You have strategic agents on one side who want a favorable prediction. You've got the decision maker who wants to minimize prediction loss. They interact via a data and model. So the strategists may in fact get to see the model because there may be regulatory reasons. If you're doing loan applications or health, you may have to publish the model, or you may have to at least tell what kind of model you're using. So people start to glean what they might do to adjust the data to get the outcome they prefer. And again, that's just going to be really part of life, and it has to be taken into account. So we have adaptation to each side of this. It is a market effectively. So the question becomes now not just what's the prediction error and how do you evaluate that, and what's the bias and all. It becomes what's the equilibrium solution, and is it a good equilibrium, and how is it achieved? Is it robust, and so on. All right, so this is a game. We're now in game theoretic land, and this has a name in game theory. This is a Stackelberg game, where Stackelberg is different from Nash equilibrium. Nash equilibrium are simultaneous games. Stackelberg are sequential games. One side makes a move, the other side responds to that move. And this is a repeated Stackelberg game. Now, who leads and who follows? And do you get what kind of results do you get depending on who leads and who follows? Well, that's interesting. So if you think of somehow the leader as having an advantage, they get to make the first move. But the follower gets to see your move and do the best thing based on your move. So sometimes they might have the advantage, but then the leader knows what you're going to do, or can predict what you're going to do. So they make their move and aware of that consequence. So it's not clear is the short answer. It depends, and you have to do analysis to think about this in particular situations. So in this situation, what's going to happen? Well, we've got a predictive model that's based on a parameter theta. We got data, let's call that, there's some measure mu, and mu and theta are the kind of the variables that are being adjusted here in this game. All right, so in step one, the decision maker announces a model. The strategic agents in step two observe the model, and they choose some measure over data. And it may cost them, there's some true data perhaps, and it may cost them a little bit to move their data. They have to pay money or do more exercise or whatever. And so that's part of the model as well, that cost. So for example, the decision maker announces a credit scoring system. People take a best response to that and try to improve their credit score. All right, so the game has dynamics in it where there's a theta vector and there's a best response. And the classical version of this is that there's one time scale, and the essential modeler responds quickest. The essential modeler is the leader, and all the strategic agents are the follower. So the strategic agents are responding as soon as a new model is announced quickly, and the essential modeler has got infinite resources, so they have the most updated model possible at every moment. Okay, but we realize that leads to one kind of Stackelberg equilibrium. But if you use different timescales, you can get different Stackelberg equilibria, and some of them might be preferable. So we should understand that. All right. So we talk about proactive and reactive decision makers. If the decision maker is slow relative to the agents, they update their model only very infrequently. We call that the proactive mode, and the decision maker can choose to be proactive in this way, or they can be reactive. Proactive models also occur in real life. For example, college admissions. The university does not change their model of admissions very often. Maybe every few years, they'll kind of adjust their criteria, and people best respond to whatever the criteria are over time. Whereas on the other hand, the reactive case is the decision maker is fast, and this is what happens, for example, in online platforms. The YouTube model or Uber or whatever is adjusted immediately based on the computing resources they have, and the strategic agents are slow relative to that. So we analyzed this kind of situation with with statistical models like logistic regression as the model, and found that in fact you get Stackelberg equilibria here. You do have equilibria. They're different equilibria depending on proactive versus reactive. And it turned out that the reactive case, this one here, where the decision maker is fast, leads to equilibria that the decision maker likes, and the strategic agents could not like. They can have very bad social burden here. All right. So you think, well, okay, maybe this is bad for, maybe the government should come in and regulate this because the decision maker is happy, but the people aren't. So you should maybe make them go back to this other model where the people are maybe happy and the decision maker's not. But it turns out that's not what the mathematics tells you. The mathematics tells you that other model actually leads to an equilibrium where both the strategic agents and the decision maker are happier. Okay, so this is actually somewhat of a surprise. It's a new result in game theory when you bring in the statistics. Both players prefer this equilibrium where the strategic agents lead. In other words, the humans are responding quickly. They're more like the college admissions model. You get better equilibrium both for the strategic agents and for the central decision maker. Okay, so that's all I wanted to say about that little research vignette, if you will. This is brand new results from this summer. There's going to be a lot more to do on this kind of problem. It really does have a game theory flavor here, but this is not the kind of game theory you'll find in game theory textbooks because we have logistic regression, we have data analysis, we have data collection, and kind of experimental design in the inner loop of the game theory. Okay, so I'm going to do another vignette. Looks like I got about maybe 10 minutes left in my talk here. If that's not true, please let me know. Work with Lydia Liu and Horia Mani at Berkeley. So again, we're going to be blending statistics and economics here. On the statistics side, we have competing bandits, or well, not just competing bandits, we have bandits. And on the economic side, we have matching markets. All right, so multi-arm bandits, presumably you all know what they are. They are really important in industry. They're, A/B tests are done with this. And again, we don't tend to teach this in our statistics curriculum, but it, of course, has in the 1950s, it was certainly studied and to this day, often in operations research, a little bit more than in statistics. Anyway, you have a number of options. An agent is trying to decide between the options, and each option has a reward associated with it. It's maybe stochastic, maybe adversarial. And you have to sample the different options and get the rewards to decide which of the choices is best. Okay, so these are unknown reward distributions, and you'd like to maximize maybe mean reward. So you have what's called an exploration exploitation trade-off, meaning that you'd like to pick the arm that has got the best reward and just do that all the time because you get high reward. On the other hand, you don't know a priori which is the best arms. You have to explore all the arms a little bit, but as you explore, you're not exploiting. So you have to blend exploration and exploitation. Okay, and so there are many algorithms that are known to be successful in this domain. One of the earlier ones is called upper confidence bound. It's very much a statistician's algorithm. So the agent forms a confidence interval on the mean reward for each of the arms based on the historical data. The algorithm then picks the arm that has got the maximal or highest upper confidence bound. So the upper confidence bound can be high for one of two reasons. One is because the overall distribution is shifted up and to the right. You have a high mean reward. It's a good arm. Or it could be that the upper confidence bound is high because you have a large uncertainty for that arm. In either case, you should pick that arm. In the first case, for exploitation reasons. In the second case, for exploration reasons. So anyway, if you pick this arm, you get an algorithm called the Ucv algorithm. And the analysis of this is in terms of regret. Regret is measured relative to an oracle who knows the best arm a priori and always picks that arm. So the question is, how well do you do relative to that? And in the beginning, you'll not do very well, but over time you should get closer and closer. And the best regrets for this problem are known to be logarithmic in the time horizon. And in particular, UCB has logarithmic regret in this problem. All right, so that's the statistical decision-making problem. Now let's put that in contact with the economics problem of matching markets. So matching markets are also pretty famous and widely used in industry. Nobel Prizes have been given for matching markets. So here you have it's a bipartite graph, buyers on one side, sellers on the other. The buyers have a known preference ordering over the sellers, and the sellers have a known preference ordering over the buyers. So this is assumed known a priori. And then the algorithm attempts to do a match where everyone is matched, as well as possible, and that's defined by a notion of stability, that there are no pair of buyer and seller who'd prefer to be matched to someone else. And there's an algorithm that achieves this, in polynomial time, a kind of bidding algorithm. Okay, so the issue here is that you really want to put these two ideas together. In real life, I will not know my preference over a large number of options. Restaurants in Shanghai, I have no idea. Even college admissions, I really don't know my preference over all colleges. So there has to be, in some ways, an information gathering process where I maybe explore a little bit the options and learn about them, and that's part of the overall matching. So let's imagine we have now a matching market where there's multiple agents and they're all exploring like an bandit algorithm. So the picture would look like this: competing agents. And now the question becomes, as they're exploring, if they pick different options, there's no problem. But what if they pick the same option? Well, in this model, there's scarcity. So you would have to sort of imagine maybe that one of the agents gets the reward and the other gets no reward. That model's congestion. So who gets the reward? Well, here the bear got the reward, and it's because arm 2 has its own preferences on the other side of the market. So arm 2 seems to prefer the bear. The human observes this and they realize, oh, I see, I like arm 2, but the bear does also. And when I pick arm 2, I tend to lose. So I better explore some of the other options more than I otherwise would. So competition seems to be leading to an increase in regret here. And the question is that really true? Can you analyze that? And what's a good algorithm for structuring this kind of statistical market? All right, so we've studied this and we call these things bandit markets. It's kind of what I've already said. And now to analyze this, you need to define a notion of regret. I don't want to get into the detailed notation here, but basically the oracle is that you assume you knew the preferences a priori, like in the classical case, and you did a Gales-Shapley matching. What is your regret relative to that as you're doing the learning? Okay, so we call that the stable regret. And we'd like to minimize this. All right, so we've studied a number of algorithms. Here's one particular algorithm. This is called Gale-Shapley upper confidence bound, and it's just is gluing together of the ideas I've already presented. So each agent has a confidence interval on each arm, and they send the upper confidence bound for each arm to Gale-Shapley algorithm. It runs and does a tentative matching, and then people get a reward from that matching and adjust their confidence intervals based on that matching, and the algorithm iterates. Okay, so this can be used in real life problems. Does it have good theoretical properties? And the answer is yes, it does. It has actually logarithmic regret. So the regret does go up a little bit, and that's because of this delta squared in the denominator. That's a measure of the overlap among the probabilities, the reward distributions. So if you have small overlap, you get a larger regret, which makes intuitive sense. But it's only a constant. The regret overall still scales in the time horizon as logarithmic in the time horizon. So this says that you can effectively learn in this multi-agent setting, and the overlap among agents does create competition, but it's only a constant. Okay, so that's the second problem that gives you a little bit of a flavor of statistical decision-making meets economics sort of setting. It's a little bit of a stylized problem, but it's kind of already generating a lot of research, and problems of this kind, statistical decision-making in multi-agent setting, I think are going to become more and more common because they reflect real-life considerations. I think I'll do this one more, and then I'm going to close up. So again, work with students at Berkeley. So auctions are a classical bit of microeconomics. You don't see a lot of them in statistics, but they are a data gathering mechanism. They try to gather this notion of a private valuation, that if you knew my valuation for things, you would probably give me a better service. At least you might give me the item I like. But I have this held privately. I don't want to just give you this data. So I want to use an auction to sort of reveal your preference without over revealing. Okay, so optimal auctions have been designed in economics. There are, again, Nobel Prizes given for this, and they're used in real life. They, again, aren't very statistical. They assume a priori, the auction designer knows a priori, not the valuation, but they know the distribution on the valuations. These are called Bayesian auctions. In real life, you don't know the distribution on the valuations probably. But in a repeated setting, you might be able to form an empirical estimate of that. And the question is, if you plug in that empirical estimate, you get a good auction. But the real question is, this is an adversarial situation. We have strategic agents. Probably we're not going to get out IID data. Probably they're going to shape their data to be different. And the question is, do you still get out an effective auction? Okay, so we have this question then of robust estimation or learning of an optimal auction. And the question is, can this even be done? And again, I'm not going to get into details. We have a paper on this that you can see on my website. But just to say we're able to do this. And so we have defined an empirical Myerson auction that's putting together statistics with economics. Empirical just means we're using data, and Myerson auction means we're using classical economic theory. And we're able to show that our version of it is robust. The classical empirical, the plug-in estimate is not. But we have a particular robustification that is robust to any distribution within alpha of the true distribution in KS distance. And let me just say a little bit more about what that means. Here's just briefly our model. Bidders have true evaluation distributions, D star, but samples are drawn from corrupted distributions, D tilde. And we assume that you're within an alpha factor in Kolmogorov-Smirnov distance, i.e. you can move arbitrarily the mass of the probability distribution up to a level alpha. So this is a pretty good model for an adversary. You can allow a complete change of the distribution up to level alpha. And here's a theorem that says your revenue from the auction is within a factor of 1 minus alpha of the revenue you would get out of the optimal auction. And at the bottom of the page there is a sample complexity. How many samples do you need to collect to achieve this level of performance in your auction? Okay, so this is really bringing together statistical inference ideas with auction design issues. Okay, I'm going to finish here. I think, there's an algorithm sketch here just to say this is the empirical auction it uses a lower convex envelope of a piecewise constant function. So there you're actually bringing in kind of, statistical ideas of how to estimate piecewise constant functions and so on. Okay, there was a last project which I've decided I'm not going to cover, but this has to do with back to kind of bandits and matching markets and quantifying equilibria here. So equilibria in economics is usually a binary notion. You're either stable or you're not. If you want to do statistics with things, you got to kind of turn those notions into something like a smooth curve you can optimize. And so we have a smooth notion of equilibrium. And so this paper with my students at Berkeley does this. So I'm going to skip that. Okay, so I'm going to finish just by returning to this slide, which I set up in the beginning, that this field that, again, if you want to call it statistical engineering, if you really want statistical engineering to have a very, very broad scope, it should be at least the scope that's being used for machine learning in industry. Meaning I take in data, I build large-scale systems, platforms that make services for people based on that, and I try to make guarantees the overall system behaves effectively for people. And so partly that's just kind of learning to make predictions and doing statistical analysis and having pipelines that do that, but partly it's putting that closed loop and multiple agents perspective into play so that you have economics as well. And I do believe this is the emerging phenomenon of the real world. It's very different than just sitting down with a scientist and analyzing their data, or looking at just a data set that someone in industry gave you and you had to analyze it and give back a plot of some kind. But I think this is the real engineering problem, is to design systems that do these kind of things. And again, returning to my slide about chemical engineering, someone who designs a chemical factory is not just designing one flow and one pipeline. They're designing the entire factory, and it has its feedback loops, it has its processes, it has its timescales, and it's the design of that factory which is the key, and not the design of just a single pipeline. All right, thanks very much for being an audience for me, and I look forward to further discussion today.
Thank you very much, Professor Jordan. That was really, really exciting, really insightful. We do have a couple questions here, so I'll just read one from the chat. This is from Christine Anderson-Cook. Her question is, in the vignettes that you shared, the goal seemed to be to find a single best solution with a clear winner. How easy is it to identify the winner in the context of several competing objectives for each participant? It seems like that might be a relatively common context.
No, absolutely. It's a great question, and that certainly would expand the scope of my talk by another hour. And so we have worked on that. We have kind of Pareto optimality kind of notions, but extensions of them for statistical purposes. So we also have notions of exchange economies and so on. So as I'm sure you're aware by asking the question, economists are definitely all over multi-objective kind of situations. And so partly we borrow their thinking, but we have to, again, adapt it to our setting. The problems do become harder, and often there is not just one answer. As you allude to, there might be trade-offs, and you want to reveal those trade-offs. So part of being a good system to me is not just that you optimize and you're done and it's a black box, but rather you're sort of transparent with the users. What are the options? What are the trade-offs? And you're also transparent about what everyone's getting out of it. So I want to participate in the system. I don't feel like I'm being treated badly. And in fact, this kind of word of equilibria, though, even though you're absolutely right, it's not itself enough. It's, I think, in many ways better than optimum. We often use the word optimal a lot in statistics. Optimal is often just unachievable, whereas equilibrium is maybe something a little more achievable. But as you point out, even softening that a little bit is important.
Excellent, thank you. So another question, you talked sort of about the synergy between combining different schools of thought and different disciplines, but I think our university curriculums don't really do that very well. And so I'm wondering what your thoughts are on how current statistical curricula need to change or adapt sort of in the response to these more modern problems that we're trying to solve.
Yeah, no, that's a great question also. So first of all, let me just, I didn't really mention David Blackwell here. So let me just say that, anyone with a little bit of gray hair, remembers some of these issues back in the day. And I got to know David Blackwell when I first came to Berkeley. None of what I talked about here would be a surprise to David Blackwell. He worked simultaneously in statistics and economics and computation. And there's Blackwell theorems in each of those fields. So I don't think he perceived a difference between these things. He already had this. And moreover, you know, the people of that era, Bellman or even von Neumann, et cetera, similarly, they were kind of mathematicians coming into game theory. Statistics was all part of the same, part and parcel of the same thing. So in that era, there was a unity in their thinking style, at least, and then it split apart. And somehow, you know, computation took just the programming language side, and you know, bits in the computer, and you know, economics took a certain set of things, and statistics took kind of linear regression. And yeah, but really, they should have been all together all the time, and they're having to come back together by the real world challenges. You know, so that said, you know, a few years ago, I got together with colleagues at Berkeley, and we designed a new program, a new undergraduate curriculum for data science, and it's had some impact. And me and the two colleagues that were most involved in the design, we wrote an article in the Harvard Data Science Review earlier this year. It's called Computational Thinking and Inferential Thinking, you know, Design of Data Science Curriculum at Berkeley. And I would point to that. I would love it if people here would read that. You know, that was before I had a lot of economics in my thinking, but by the end of the undergraduate sequence, you arrive at economics and game theory and matching. But anyway, it starts with you know, a very computational view of statistics, that, you know, permutation tests and bootstraps and all are highlighted, and asymptotics are not. So you learn, for example, the inferential problem is to compare two columns of numbers. The approach is going to be to you know, put them together in a big column and do a permutation and then get a sampling distribution. And you can learn to program that in your favorite programming language, Python or whatever. So we teach them the Python, we teach them the permutation test, we show the histograms, and then we work on real data, and then we move to another little vignette, if you will. That's in the freshman level. So that was the design of that class, and students loved it. We get, you know, now nearly 2,000, or actually up to 3,000 students a year taking this class at Berkeley. And it doesn't do a lot of mathematics, but there's mathematical concepts pervading it. There's real data analysis, and they're doing engineering kind of building of things. And by the time they get through the curriculum, they've built bigger systems, and they've learned a lot more inferential principles. So to me, that doing that at the undergrad level was actually eye-opening and revealing. You don't have to just try to take all of statistics and blend it with all of computer science. You throw away a fair amount of the older part of statistics. In fact, a lot of the asymptotics is not really relevant. You replace it with the computer does the computation, and you get a win-win. You can now teach the more advanced methods at the freshman level, and students actually like it because they can deploy it themselves. And I do think that the econ thing is not that hard to bring in as well. Like a matching market's a nice little cute algorithm. You can teach that as well. So long story short, I think at the undergraduate level, a lot of us can and should cast aside and redeploy a brand new curriculum there. And that requires buy-in and lots of effort. We did that at Berkeley, where it's still a work in progress. But I think that's what's needed. And the grad level, I mean, I just think a lot of the students already get this, and just kind of, you know, open up the curriculum and let them take courses in computer science and economics, let them blend it in their own way. But I think the undergrad curriculum is, so data science helped get leverage on this, and I think maybe that's still a good terminology going forward. You know, but I would just sort of blend in a little bit of the econ, and I think you're kind of good to go.
Yeah, great, thank you. Well, I see there's a couple other questions, but I want to respect your time. We have a panel discussion coming up in 5 minutes that you're also a part of, so I want to give you a chance to have a break. I think those of you who did ask questions that weren't answered, I'm sure Dr. Jordan would be happy to respond to them by email later at some point, or if we have time later in the program, we can maybe come back to it. But for now, I just want to thank you on behalf of all of us in the audience, Dr. Jordan, for your talk and for your time. So with that said, let's spend the next 5 minutes or so having a quick break. At 11:10, we're going to come back with the panel discussion where we address the past, present, and future of statistical engineering. Thanks, everybody.